Hello students, in this video we'll consider the Euler numbers. We'll do so by considering the following function. Consider the function f of x is 2 e to the x over e to the 2x plus 1. This function is analytic at the origin, so it has a Taylor expansion. So I can write this down. This has a Taylor series, and the Taylor series is written in the form n goes from 0 to infinity, okay, of x to the n, that's the power, and we have these numbers en x to the n over n factorial, and so these coefficients of this Taylor series en are called the Euler numbers. So here the sequence n goes from 0 to infinity are called the Euler numbers. Okay, these Euler numbers are going to come up in important Taylor series we'll see in a second. So where do these Euler numbers appear? Well, notice that f of x, if I multiply the top and bottom by e to the negative 2x, so if I look at f of x, which is 2 e to the x over e to the 2x plus 1, multiply top and bottom by e to the negative 2x, that won't change anything. The top will become 2 e to the negative x over, this will turn into a 1 plus e to the negative 2x, which is f of negative x. So I've just shown that this function f of x is an even function. So f is even. So f is even. And we know that for even functions, all of the odd Taylor coefficients are 0. And so now I can conclude from this that e to n plus 1 is equal to 0 for n equals 0, 1, 2, etc. All of the odd Euler numbers are equal to 0. Okay? That's the first observation we're going to make about the Euler numbers, that all the odd ones are 0. So of course this function is an even function. Now I can relate this function to some well-known functions, because in particular what I can do is this. I can multiply now f of x, which is 2 e to the x over e to the x plus 1. I'm going to multiply by the top and bottom by e to the negative x this time. And this will turn into a 2 over e to the x plus e to the negative x. And this is 1 over the hyperbolic cosine of x. And so this is called the hyperbolic secant of x. And we're going to see this function actually over here has very important Fourier analytic properties. So hyperbolic secant of x. And now what I'm able to do is I'm able to say that hyperbolic secant of x is represented by this formula over here. It's the sum. N goes from 0 to infinity. Of what? Of e0, of just e2n, x to the 2n over 2n factorial. We can write it like this over here, okay? So we'd like to find these Euler numbers over here. Of course, we can clearly see that the 0th Euler number is just the secant of 0, the hyperbolic secant of 0, which is going to be a cosh of 0 is going to be what? If I plug in 0 to this, I'm going to get a 2 over 2, so 1, so the e0 is going to be equal to a 1. Good? Okay? All right, and so now what are some other important properties of this? Well, notice now that if I plug in I to this formula, so if we look at f of ix in particular, what this is going to be, this f of ix is going to be, according to this formula, 2 over e to the ix plus e to the minus ix, right? And so what that is, that's just going to be 1 over, that's just the reciprocal of cosine, so this is just secant of x. So therefore we get the Taylor expansion of secant, so I get when I plug in I to this formula over here, so I'm going to have n goes from 0 to infinity of e to n, and then ix to the 2n over 2n factorial. And this is what? This is the sum, n goes from 0 to infinity of negative 1 to the n, negative 1 to the n, x to the 2n over 2n factorial, okay? And we'll later on see, using some complex variables techniques, that this series is valid if x is less than pi over 2, right? That's when we have some potential have some singularities, okay? So that's the region of convergence. All right, great. And so now I get one more result from this. We know that the integral of secant is the natural log of secant x plus tangent x, okay? That's an antiderivative of secant, integral of secant of x dx. And so up to a constant, of course. And so I can just integrate this series and conclude that the sum, n goes from 0 to infinity, of the 2n Euler number, x to the 2n plus 1 over 2n plus 1 factorial is the Taylor expansion for the natural log of secant x plus tangent x at the origin. Now, one final comment from this is that what we could do to find a recursion relationship for these things over here is we can say that's 2 times e to the x. So we know that 2 times e to the x, 2e to the x, that's the top over here, is equal to this sum over here, n goes from 0 to infinity, of 2 to the n, so e to the 2x is 2 to the n, x to the n over n factorial, and then plus 1 times these what? Times these Euler numbers over here, n goes from 0 to infinity of just en x to the n over n factorial. And so what I get from this is I know that this thing has a Taylor expansion. This is going to be 2, the sum n goes from 0 to infinity of x to the n over n factorial. What we're able to do from this is that if I multiply these expressions out over here, I will get a recursion relationship for these Euler numbers over here. So by comparing the coefficients in this Taylor series with the coefficients in this Taylor series over here, I'll be able to construct a recursion for these Euler numbers, which has the following form. The form of this is going to be 2 plus e to the power n. And what I mean by this is I mean that whenever I'm multiplying e to the power n, I'm going to treat that e to the any power k is e sub k in this, is equal to, is roughly equal to, according to this notation over here, is equal to what? Is going to be equal to just a plus e, of course, is going to be equal to 2. So there's going to be plus e to the n, so plus e to the n, well, that's e sub n, of course, plus e to the n. It's just going to be equal to the coefficient over here, which is just going to be a factor of 2. And so that's this recursion relationship. If you plug in a couple terms over here, you'll be able to generate all the Euler numbers, and you'll be able to find the Taylor expansion of secant, the natural log of secant plus tangent, and a variety of other Taylor expansions. Thank you very much.